Assalamualaikum and hello. Before I start, I will introduce you to my group members. First, we got Ahmad Hafizi Ikhwan bin Azhar. Second, we got Emil Ishkar bin Muhammad Ramadan. Third, we got Muhammad Syabihaka bin Arizan. And fourth, we got Muhammad Hakimi bin Muhammad Zini. And I'm Muhammad Syabihaka bin Arizan, your presenter. Today, I will present my assignment about a traffic light system design. Traffic lights are very important in controlling the movement of vehicle at road intersection. They help reduce traffic congestion and prevent accident by organizing the flow of traffic. In this project, I designed a traffic light system using a sequential circuit with D flip-flops. The design includes a flowchart, state diagram, state table, and sequential circuit design. Traffic light control system is a fundamental practical application in the field of digital system and sequential logic. Technically, a traffic light functions as a finite state machine (FSM) that transitions through a sequence of specific phase, green, yellow, red, in a repetitive cycle. In this project, a 3-bit synchronized counter is designed to control this transition. Using a 3-bit system allows for distinct state, providing enough resolution to manage the timing of each light color. The core component utilized is the D flip-flop, chosen for its simplicity in implementing next state logic. Since the input of flip-flop directly represents the desired output of the next clock cycle, it allows for more straightforward mapping from the truth table to the physical logic gates. First, this is the flowchart of the traffic light system. The system starts with the green light, which allows vehicle to move after a certain period of time. The light changes to yellow to warn the driver that the signal will change soon. Finally, the light turns red, which means vehicle must stop. After the red light, the cycle repeats after again starting from green. Next is the state diagram of the traffic light system. The system uses several states to represent the different light conditions. For example, state 0 to state 3 represent green light, state 4 and state 5 represent the yellow light, and state 6 and state 7 represent the red light. The states change sequentially according to the clock signal until the cycle repeats again. The state table shows the relationship between the present state and the next state of the system. It also shows the output for each stage, which determine whether the green, yellow, or red light is turned on. This table helps us understand how the system transitions from one state to another. Finally, the sequential circuit design is developed using D flip-flop. The flip-flop store the current state of the system, while logic gates determine the next state. This design allows the traffic light system to operate automatically and change state based on the clock input. In this logic circuit, the first D flip-flop can be represented as a red, the second D flip-flop can represent as yellow, and the third D flip-flop can represent as a green. This is a circuit waveform. There is a clock, there is a clear, and there is an output of Q2, Q1, and Q0. This is the explanation of a traffic light. Start. The traffic light system is power on. Green, the green light is turned on, allowing vehicle to move. Yellow, the yellow light is turned on, warning vehicle to slow down and get ready to stop. Red, the red light is turned on, requiring vehicle to stop completely. Loop. After the red light phase ends, the system will return back to green, and it will repeat continuously. In conclusion, the design of a 3-bit traffic light system using D flip-flops effectively demonstrates how digital logic theories are applied to automate control system by developing the truth table and performing K-math. Analyzing the excitation equation for each input was successfully derived to ensure the binary sequence 00 0 to 111 operate accordingly. The result of the project confirmed that T flip-flop are highly efficient for state machine design because the input requirements are identical to the desired next state, simplifying the combinational logic circuit. A 3-bit configuration provides sufficient flexibility to allocate specific time interval for each leg. Example given: green for 4 states, yellow for 2 states, and red for 2 states. Precise clock synchronization is critical to ensure that the state transition occur without timing hazard or glitches. And that's all from me. Thank you very much.